Let f of x be equal to a square root of 1 plus x shows that the second derivative is equal to a given expression. To find the second derivative, we should find the first derivative firstly. So we can see that f of x is 1 plus x to the power of a half, and hence we should apply a chain rule, and it says that it becomes a half 1 plus x to the power of a half minus 1, which is negative a half, and multiplied by 1 plus x derivative, which is just 1, and hence the second derivative becomes a half negative a half 1 plus x to the power of negative a half minus 1, which is negative 3 over 2, and multiplied by 1 plus x derivative, which is 1, and finally it's negative 1 over 4 square root of 1 plus x cubed as required. The next, use mathematical induction to prove that the nth derivative of f is equal to a given expression, and we can see that n is greater or equal than 2. So we start with the smallest value of n, so we write for n equals 2 for the function of the second derivative is equal to negative 1 over 4 root 1 plus x cubed. It's the result from A, and from the statement just substitute 2 for n into a given expression, and we can see that it becomes negative 1 over 4 to the power of 1. 4 minus 3 is 1 factorial, it's 1, over 0 factorial, which is also 1 plus x to the power of a half minus 2, which is negative 3 over 2. So we can see that, or we can rewrite it, and it is equal to negative 1 over 4 root 1 plus x cubed, hence true for n equals 2. The next step is, as usual, we write assume true for n equals k, and just rewrite a given statement substituting k for n. So assume true for n equals k. Hence f, and the derivative is number k, becomes negative 1 over 4 k minus 1 to k minus 3 factorial over k minus 2 factorial 1 plus x a half minus k. And the next step is, as usual, we consider for n equals k plus 1. Hence it becomes the derivative with number k plus 1 of f, and it's the derivative of the derivative with number k. So we can rewrite it as f k of x derivative, and substitute this expression for f k, and hence it becomes, since it's some constant, we can write it just in front, so it becomes negative 1 over 4 k minus 1 to k minus 3 factorial k minus 2 factorial and 1 plus x a half minus k derivative. Notice that k is constant because it's the derivative with respect to x. X is a variable, and it is equal to negative 1 over 4 to the power of k minus 1 to k minus 3 factorial over k minus 2 factorial, and what is the derivative here? It's again a half minus k, 1 plus x, a half minus k minus 1, and multiplied by 1 plus x derivative, which is 1 according to the chain rule, and it is equal to, and let's write here what should we get. You don't need to write it. So we should finally get here negative 1 over 4 to the power of k plus 1 minus 1, it's just k. 2k plus 1 in parentheses, hence it's 2k plus 2 minus 3, it's 2k minus 1 factorial over k plus 1 minus 2k minus 1 factorial, 1 plus x, a half minus k, k plus 1 in parentheses, or k minus k minus 1. So we can see that it's as required, and my idea is the next. Let's multiply and divide this expression so that we get what we need, and then we just simplify all other factors. What do I mean? Since we need negative 1 over 4 to the power of k, and we have negative 1 over 4 to the power of k minus 1, it means that there is negative 4 in the denominator, and we can multiply by negative 4 the numerator and the denominator. It's just 1. And since we need 2k minus 3, we have 2k minus 3 factorial, and we need 2k minus 1 factorial. What is 2k minus 1 factorial? To get 2k minus 1 factorial, 2k minus 3 factorial must be additionally multiplied by 2k minus 1, 2k minus 2, and 2k minus 1. But I cannot just multiply by these factors, by these terms in numerator. I should also divide. If I multiply and divide, it's just 1. So this expression remains the same. But finally, it's as required in numerator. And we have k minus 2 factorial, and we need k minus 1 factorial in the denominator. How to get k minus 1 factorial? Just multiplied by k minus 1, because k minus 2 multiplied by k factorial multiplied by k minus 1, it's k minus 1 factorial. But also I should multiply in numerator, because it's 1. And other terms, let's make here a common denominator. It becomes 1 minus 2k over 2, and actually it's maybe used for instead of this actually, but it's not important. And multiplied by 1 plus x to the power of a half minus k minus 1. It will be more simply if we use this instead of this, but that doesn't matter. So it becomes negative 4 goes to this expression, and finally it becomes negative 1 over 4 to the power of k as required. And this and this becomes 2k minus 1 factorial. This together with this becomes k minus 1 factorial, and remaining terms are k minus 1 here, negative 4 also, negative 4 in numerator, k minus 1, 2k minus 2, 2k minus 1 here, and 1 minus 2k over 2, and 1 plus x, a half minus k minus 1. And we can see that we can factor, let's rewrite, 2k minus 1 factorial, k minus 1 factorial, and we need simplify it, and you can guess that it must be 1. They must cancel. So, and let's just show it more clear. Negative 4 k plus 1, we can factor negative 1 here, so it becomes negative 1 2k minus 1, factor out 2 here becomes k minus 1, 2k minus 1, and 2, 1 plus x, a half minus k minus 1. And now it's clear that it's just 1. And finally we get negative 1 over 4 to the power of k, 2k minus 1 factorial, k minus 1 factorial, 1 plus x, a half minus k minus 1, and you can see that it is equal to the expression to this when n is k plus 1, and it's directly like this. So hence true for n equals k plus 1, and the conclusion: if true for n equals k, true for n equals k plus 1. Since true for n equals 2, true for any n is integer and greater or equal than 2. The next question. Let g of x be equal to e to the power of mx. Consider the function h, which is the product of f and g. It is given that the x squared term in the Maclaurin series for h has a coefficient of 7 over 4. Find the possible values of m. So, since it is given the Maclaurin series, let's consider what it is. So, the Maclaurin series for h is the first h of 0 plus the first derivative at 0x plus the second at 0x squared over 2, and hence the second derivative at 0 over 2 is equal to 7 over 4. It is given, and to use it we should find the second derivative of h firstly, and let's consider the first derivative firstly. So h primed becomes, we can see a product, so we should apply product rule. It becomes f derivative times g plus f just f multiplied by g derivative, and the second derivative becomes the second of f multiplied by g plus f derivative g derivative, and plus here it becomes f derivative times g derivative, I write 2 here, plus f of x multiplied by g, the second derivative. And let's continue. So the second derivative of f it's this. It's negative 1 over 4 square root of 1 plus x cubed multiplied by g, it's e to the power of mx, plus 2, the first derivative, it's a half 1 plus x to the power of negative a half, multiplied by g derivative, it's m e mx, plus f, it's square root of 1 plus x, multiplied by the second derivative of g, which is m squared e to the power of mx. And h, the second derivative, at 0 becomes negative 1 over 4 plus m squared, and it's 2 multiplied by 7 over 4, or just 7 over 2, and hence we can see that we get a quadratic equation and we need just solve for m. So let's multiply by 4 each term and get 4m squared plus 4m minus 1 minus 14 is 0, which is just minus 15 is 0, and let's use discriminant, which is b squared minus 4ac, so it's 16 minus 4 times negative 15, and we can see that we can factor out 16, it becomes 16 times 16, hence roots are minus b, it's negative 4 plus minus root d, which is just 16 over 2a, 2 times 4, and it's becomes negative 1 over 2 plus minus 2, which is negative 2.5 or 1.5. And that's all for this question.